Our next topic is marketing for mobile gaming. And the speaker is Michal, who is data scientist at Nordeous. He's bachelor in mathematics at the University of Wrocław, PhD in mathematics of University of Bonn, and currently a data scientist at Nordeous since 2018. I invite you and give you the stage.
Okay, can you hear me? I guess you can. Thank you so much for the introduction. Yes, so as already mentioned, today I'll be talking about predictive modeling in marketing for mobile gaming. So let me just start with a couple of slides. Let's see if this is working. Yeah, just a couple of slides about Nordeous and our data science team. So Nordeous is based and founded here in Belgrade in 2010, and from June 2021 also part of Take-Two. We have close to 200 employees from all over the world, and currently 2 live games, Heroic Magic Duel and Top 11, which is our most successful game, which brought over 250 million registered users worldwide. We have Jose Mourinho as our brand ambassador, and even though the game is already 12 years old, it's still very successful and growing. For instance, since this year, you can also play it in 3D. Now, regarding our data science team, so except for this topic we'll be talking about today, so predictive modeling, some other topics that our data science team is interested in and deals with on daily basis is, for instance, A/B testing, recommender systems, as well as reinforcement learning, computer vision, and generative models. And now, predictive modeling in marketing. So again, just zooming into this area, it's still quite broad actually. So just to list a couple of problems that you can come across there. There is LTV prediction, K-factor modeling, as well as marketing mix modeling, payer prediction, churn prediction, so on and so forth. So this presentation will be structured as the following. So we'll start with discussing LTV prediction and then K-factor modeling. In more detail, this will be like the 2 main parts of the presentation, and later on also have the variant of the presentation also briefly discuss what the other topics mentioned here are about. All right, so starting off with LTV prediction, just to make sure we're all on the same page, just to define everything that's happening here. So customer lifetime value prediction, which is known as CLV, or lifetime value prediction, which is abbreviated as LTV predictions, are really the same thing. You can find both namings in literature. And the answer, the question we want to answer here really is like, so given historical data of a customer, so say in our case, it's mobile gaming, so a user that installed our game, say, 7 days ago, and had some all kinds of interaction with the game, so some transactions, but also like playtime, session, and so on. So giving all this historical data, what can you say about the future amount of money that this user, so the revenue that this user will generate, for instance, in the next 6 months or 12 months or something like this. So we'll discuss approaches to LTV prediction, in particular the ones we use at Nordeous and also its applications in the gaming industry. Okay. All right, so now a little bit more detail. What we mean by LTV prediction in gaming is that, well, as I said again, we have some user registering in the game on some day X, then up to day X plus N, so in the first N days in the game, so say, and it's like first 7 days, the user has all kinds of interactions in the game, spends some money possibly, but also has some number of sessions. We collect all this data. And then after these first 10 days, we ask ourselves, what is the expected total revenue generated by this user in the next 10 days? So this is it's actually looking for revenue on this day. So we have user U and total revenue on this day. So this is just, we define this quantity. And this is so-called user-level LTV prediction. And now what we're actually usually more interested in marketing is the so-called cohort-level LTV prediction, which is like similar to the above, but except for looking at the single user, we take, say, all the users that registered on the same day X, and then ask the same question, but we ask, like, what is the average revenue or average LTV generated by the set of users after the next M days. So let's say total 1 year in the game or something like this. So it's just basically similar as the above, we just take the average. All right, so now, this is the, right. So now the basic object that you study when doing LTV prediction is the so-called LTV curve. And this is basically this quantity that we saw in the previous slide. So let's say with some group of users, cohort of users that registered on some day X, let's say we have 1 year of their data in the game. And what we're doing is just we take each day from 0 to 365, we take the average LTV, average revenue of this group of users on every day, and this way we like build a curve like looking like this. And this is called the LTV curve. And now it's just important, like we shall see, it's important later on in this talk as well, is that typically this curve has this logarithm-like shape, and it's also, well, because mobile gaming industry is in general quite dynamic, things change quite quickly, which also means that the actual final average LTV value for a cohort of users, so let's say on day 365, as well as the growth rate, so how quickly this curve is growing, can really vary a lot from cohort to cohort. And this is also one of the reasons that make this problem difficult. And now on the importance of LTV prediction in marketing, is basically, well, given that we have an LTV prediction tool that is reliable, we can quickly say something about profitability of marketing campaigns. So say we have 2 marketing campaigns, A and B, and we would like to say having an LTV prediction tool that works reliably, let's say already after a couple of days, we can quickly compare whether campaign B is performing, whether campaign A is performing better than campaign B or vice versa. So in general, we can say something about return on investment of marketing campaigns with some confidence. And now this LTV, so this was more about this cohort level LTV prediction, and on the user level, if we have LTV prediction tool on the user level, then this can be also used for some recommender system where you can early on distinguish potential high spenders and low spenders, and then just appropriately personalize and improve their experience with the game. So in general, to answer these questions above, we would ideally would like to have LTV prediction that works already after several days in the game, sorry. And the prediction horizon that we would like it to be as wide as possible. So typically, marketing teams need 6 to 12 months to make it usable. All right, and now I have a couple of slides about why LTV prediction is a difficult problem. So first of all, I listed just a couple of reasons here. So first of all is sparsity. So as was already mentioned here today in the morning, most of the users that install our games, so this apparently in general in various industries, but especially in mobile gaming, most of the users will never spend any money. So the distribution, you can imagine that will look something like this approximately, where most of the users will not spend any money, and then we have a fraction of payers. And then another thing is that the behavior of payers can vary really a lot, meaning that they spend this, by the way, the log scale, so their behavior can vary a lot. The other problem the other difficulty with LTV prediction is the so-called distribution shift. So we're quite used to that in ML, usually we say we learn some mapping from X to Y, so we train some, I don't know, linear regression model or neural net to map input to outputs, and then we take some historical data, we train the model, then we deploy it, and we kind of assume that distribution that we have for inference is either the same or very similar to the ones we had during training. Now the problem is that with LTV prediction we cannot, if we want to have predictions with like long time horizon, we cannot really frame this problem like this because, well, the reason is, so say we're somewhere here, so this is basically average LTV of, so this is like the time axis. Here we have the average LTV of a cohort after 365 days. So actually this is something we want to predict here, but we still don't know it really. And if we were to frame this problem as x to y mapping, then what we would really have to do is to go to this blue region, which is already 1 year or 1 or more years, or at least 1 year delayed, which means that, especially, so again, in mobile gaming industry, things change quickly, so this can be completely different distribution up to this point in time. So this makes it pretty useless at this point. So we have to do something else. Now, yet another problem is, well, kind of related to the previous slide. So let's say I have some model and I have some features that I would like to use in this model, where the thing is with the features, but again, this distribution shift that we discussed, distribution of any feature we'd like to use can change a lot. So we have kind of, well, basically be careful. And also if our features of our model are maybe too much related to some game modes, the game can change a lot within a couple of months. So it might happen that like features I would like to use are stop existing or just become useless. So we have to be careful. And well, although we, in general, in statistics and ML, well, to prevent overfitting, here it's, I mean, you have a problem with a LTV prediction that directly impacts marketing spend. So we kind of, in some sense, would like to prevent this at all costs. Meaning that we'd like to, of course, have a flexible model, but also not to overcomplicate things to prevent overfitting. So this is also quite important to keep in mind here. And just a short note, because in literature, you have successful applications of this X to Y ML models like random forest, regression, or neural nets to LTV prediction, but this is either for industries that are not as dynamic as mobile gaming, or they deal with short-term predictions, like let's say what will happen the next month, which is kind of, then maybe you can get away with this problem of the distribution shift. All right, so I listed a couple of things that make it difficult. So the LTV predictions, so just to sum it up, ideally would like a model that handles sparsity well, meaning the sparsity of pairs among non-pairs, then adapts well to distribution shift in time, and then that uses relatively modest like number of features that are ideally like transaction related, so quite general. All right, so now I would like to discuss two approaches to the problem, and now the first one is the simpler one of the two, and it's called the so-called curve fitting, which you might heard of already, but let's just go through this slide quickly. So for linear regression, what's happening, like the simple linear regression looks like the following. So we have some data points that are like these blue dots here, and then you want to find the best line that passes through these points, so like this red line here. And now for curve fitting, the situation is similar. However, instead of looking for the optimizing within some linear family of functions, in this case lines, we're optimizing within some nonlinear family of functions. For example, some log-like curves, or maybe some polynomials up to some degree, or something like this. So this is in general for curve fitting. And now the idea of using curve fitting for this problem is simply to take, well, we have a cohort of users that registered n days ago. We take, like, let's say the average LTV, so the average revenue of this group of users, and then like these first n days. And then if we have some domain knowledge of what this LTV curve, like how it evolves, it can look like in the future, then we basically can fit a curve through these points. And given that our assumptions make sense, and we have many data points, we can just extrapolate this to obtain prediction for any day in the future. So just basically we do this. And now the thing is that I said we need some domain knowledge about this problem, but we already discussed this in mobile gaming, this LTV curve usually has this log-like shape. So then you can try to fit, actually this choice is, by the way, not a bad one to start with. So we can parameterize this curve, for instance, like with logarithms, with 1 or 2 parameters or something like this, something similar. And now the great thing about it is that it's a really simple model. So it's easy both to implement, and then also the optimization is fairly quick. So you can quickly pass through like big data set using this method. So again, it looks like the following. Let's say in this case, we have we have some cohort of users. We have, let's say, here's about, I don't know, like 40 initial points on this LTV curve. So this is what we know up to day 40. And then, well, if we fit some log-like curve, say, through these points, we extrapolate. So we extrapolate this orange line. And then as the time goes by, we can basically compare our prediction, so the orange line, with the actual LTV value, which is the blue one, to track its performance. And now, so about some pros and cons of curve fitting. So first of all, like all these requirements we had regarding it, like sparsity, distribution shift, and simplicity are of course satisfied. Like for instance, for sparsity, we don't really see that problem because we work only with averages. So we don't really see the actual LTV distribution, so it's not problematic. Then for distribution shift, again, we don't have this problem because we take only the current cohort that we work with. We don't care about any historical data at this point, so we're not biasing our results in this way. And then, yeah, it's of course simple. We have only one feature. It's curve fitting, a very simple model. And now the performance of the model is actually, because it's a very simple model and it's surprisingly good. However, it's good if you have enough many data points, meaning that, okay, I don't mean that you need like, I don't know, 200 days to work well for 1 year, but you need like around for our data, for instance, in Nordeous, we found it to be around 2 months of data for this to be reliable. And now this brings us to the other approach I wanted to talk about. So I call here probabilistic models. So basically the main problem we want to solve now is that, well, we don't want to wait 2 months to make predictions. We would like it to work already, let's say after 7 or 14 days or something like this. Okay, and for this, just like a quick intro, there will be some similarities to curve fitting here actually, in the sense that, again, we won't be learning an explicit X to Y mapping, but rather we'll use some domain knowledge about the problem to fit some distributions and then basically to extrapolate the curve. So we'll make assumptions about how the LTV curve evolves. So this is some domain knowledge that we're going to use. And the difference will be also that instead of using only one single feature that was the actual value of average LTV, we'll be using a couple of features. So it will be a bit more complex model. All right, so now the things I'm presenting in this part of the presentation are taken from the paper Counting Your Customers the Easy Way by Fader, Hardy, and Lee, which is, by the way, quite an old paper already. However, this area of probabilistic model is actually quite active. There are papers coming out basically each year on this topic. And also, like another thing now, so from now on, we won't be actually talking about model that predicts the average LTV, but the average, so that expected average number of transactions for a group of users. So the full approach from this paper actually consists of, well, given some historical data, predict the number of transactions in the future, but also predict the expected average transaction value in the future. And now if you have these two values, then you can basically build the LTV curve for using this, and this is your LTV prediction. Unfortunately, we don't have time to discuss both of them in detail, and I think actually this blue one, so the model predicting number of transactions, is actually the more interesting of the two. So we'll concentrate on this one. And now some assumptions about we have to make some statistical assumptions about the transaction process for things to work out. So are the following, we have these 3 steps. So first of all, by the way, also this model now, it's a user level model, so we can work on a level of a single user. And then of course, if we have a user level model, we can just average out the predictions to obtain the prediction for the average LTV. So this is good enough. So on a user level, how it looks like, we have a user registering, meaning that the user installing our game. So this is called user becomes active. And then while active, user makes transactions with some frequency. And this frequency can, of course, depend from user to user. And then the last assumption that we make that after every transaction, user becomes inactive with some probability, meaning that they won't make any other transactions after this point. And this probability, again, it depends on the user. So it's not the same for the whole population, which is, of course, crucial here. And the features that we'll be using will be the so-called frequency, recency, and age. And how they compute it is basically, let's say we have a user that registered 7 days ago. So 7 days ago started playing our game. Then the frequency will be the number of transactions this user had during this first week. So say 5 transactions, then the frequency will be equals 5. Recency will be the time of the last transaction. So let's say if the user had their last transaction on the 4th day of activity, recency equals 4, and age is 7 because this is basically days since registration of this user. All right, so this will be the kind of simplistically what are our assumptions and the features we're using, and now just a bit more concretely how our assumptions look in the language of statistics. My point is not to go through this all in detail, but just to show a little bit about what's happening. So this frequency, sorry, this is a bit smallish, but basically what's happening is that for every user, we assume we have some parameter lambda that describes how frequently the user makes transactions, and this depends on the user. So this is for a single user. This is the cheat sheet how exponential distribution looks like for the different lambdas. So this for the frequency distribution, and then after every transaction, we assume that there is some probability with which the user becomes inactive. So then, for instance, probability that the user becomes inactive after the jth transaction follows some geometric distribution. So this is how it looks like, just a reminder. And now, so this is for a single user, but we don't really want to model a single user, but rather the whole population of users, so that later on we can do some inference. And now the thing is that we do that via priors. So the prior distribution of our frequency parameter is some gamma distribution looking approximately like this for different values of parameters. So we kind of, by sampling user, we really sample lambdas from here, and then we get different users with different behavior. And similarly for the inactivity probability, we have prior as the beta probability. So again, which this is just a reminder how beta density function looks like. So then sampling parameter from his, sampling user, basically. And now, well, you could ask, why do we actually make these assumptions? Because it's kind of complex, and why do we actually do this way and not some other way? And now the answer is that, so the answer is kind of twofold. So first of all, we need some domain knowledge about the problem, as I said. So this is basically saying that this assumption about this exponential distribution. So maybe I didn't said that. So basically, exponential distribution means that we have some lambda. That means that timings of transactions. So that assuming time between 2 consecutive transactions is exponentially distributed. So there's some domain knowledge about the problem that we use. So domain knowledge from marketing, and also which is a sensible assumption. And then we have this. Well, we assume that after every transaction, user becomes inactive. Again, a sensible assumption, but coming from domain knowledge in marketing, really. And then we have these priors here, right? So it's kind of also domain knowledge because, we have some distributions that are flexible enough or are sensible to describe different populations populations of users in marketing. But also it's actually quite crucial here that these gamma and beta distributions are chosen very carefully so that, you can imagine we'll have some statistical models, and at the end of the day, we just want to optimize the parameters of this model. And now the thing is that these distributions are very carefully chosen so that the function that we'll be optimizing at the end of the day actually has a closed form. And this is quite crucial because, you could replace gamma with some other distribution, but maybe you can run into problems not having the closed form solution. You can still do, but it's much slower and less stable to optimize than having a closed form solution. So kind of the answer is a little bit of domain knowledge, as well as choosing this carefully so you have a numerically stable function to optimize. All right, and how the optimization looks like. So it's just toy example of what's happening is really, so again, we don't have X to Y mapping. We sort of have only X's. So a toy example is the following. So we have some data sets X1, X2 through Xn. And then the histogram looks like this. Okay, it reminds us of some Gaussian distribution. So what we do then is we try to fit Gaussian in our data. And we do this by typically by maximum likelihood estimation, which is basically well, taking all our data points and just multiplying up the probability of these data points given the parameters of the Gaussian. And then we just take the logarithm because it's numerically more stable, so we have the sum of logarithms. And what we do in the end of the day is optimize this formula here down here in terms of the parameter theta. I mean, in terms of Gaussian, it's just 2 parameters actually, so mean and standard deviation. All right, so now what's happening, these two couple of slides right now, I'm aware that are a bit intense, but please bear with me. Basically, the idea here, what's happening with when optimizing our model is that, again, as I said, we had this frequency parameter for a single user. We assume it exists. And also for every single user, we assume you have this P, which is the probability of being inactive. And also for a single user, we assume we have some historical data. So this frequency, recency, and age, so number of transactions, the most recent time of the most recent transaction, and days since registrations, in other words. And now, but we don't really care about single user at this point. We care about the whole population of users. So in other words, you would like to really fit the parameters of these priors here so that later we can do some inference. And now this crucial assumption, so that this is gamma is chosen carefully and beta as well, is that when you actually write out the likelihood function for a single user in terms of just averaging out, so that in terms of these 4 parameters of the priors, so 2 for the frequency and 2 for this inactivity probability, then actually get a nice closed form function here that you can optimize. So your input data is this, and what you're optimizing are these 4 numbers. And this is what I'm saying is basically it's crucial, and it's really non-trivial computation, by the way, to get this right, that this has a closed form solution, and then it makes it much easier to optimize. And now, not only this, but also, so again, details, what's happening here is not important, but kind of, I would like just to convince you that it's also crucial that by choosing this distribution this way, we also have a closed form solution for the thing we ought to infer afterwards. So when you want to say what is the future number of the total future number of transactions of some user with this input data, and having these parameters already fit in, so we assume that we fit the model, so we have these 4 numbers. Then basically, again, we have a closed form solution for the future number of transactions, so this is what you really want to do. And, well, having closed form solution makes the inference much easier, stable, and it's actually, we don't have to approximate it, which is great. And now, comparing probabilistic models with curve fitting, basically, so first of all, again, all these requirements we had before are satisfied. So again, we deal with sparsity basically because we had these assumptions on the priors. So kind of sparsity is already hidden in the prior, so to say. We're robust to distribution shift because, again, first of all, we're not really learning X to Y mapping, but just fit this distribution to our to our data set of X's. And then, well, it's a simple model. And then, for the historical data, sorry. So in principle, we wouldn't even have to use historical data really, but we found it useful to use a couple of months of historical data to make this model more robust. So you don't have to use too much not to bias your results, which is kind of really getting rid of this shift problem. And then it's still a simple model. We have just 3 features and all just transaction related, so nothing game specific really happening here. All right, and then performance of this model is good, and it's not only good, but it also works well much earlier than the curve fitting. So we no longer have to wait 2 months. For our data, for instance, we found to be working comparable to curve fitting, or even better already after 7 or 14 days after the registration. All right, so that was it for the part for the LTV prediction. What I'd like to discuss now is K-factor modeling. So again, let's start off slowly, so just to so that everyone is on the same page. So just to define stuff. So this is where we're now shifting from kind of dealing with revenue. Now we're dealing with the number of registrations. So by paid registrations, from now on I'll mean app installs. So users that installed the app via some ad, so which can be tracked. And then organic registrations will be all the other registrations. So these ones that cannot be attributed to any advertisement. And also, well, I sometimes say install registration, but in this presentation, it's really the same thing. It's just new users starting using the app, all right? And now, what is K-factor? So K-factor is a value used in marketing used to describe app virality. And so basically, given a user that installed our app or game or whatever, we would like to estimate what is the expected number of additional users this user will bring to the game, for instance, by recommendation or word of mouth or something like that. And then, more precise in user acquisition, how we define it is, so to have a kind of a concrete formula for that, is that we have these paid registrations, so users that came to our app through an ad, and then this is something we can track, and then by having, so basically it's basically saying that if our K-factor is something that is non-zero, then we expect to, when we increase the number of paid registrations, we also expect some increase, so some incremental organic registrations. And basically, K-factor is the number that connects these two values, these incremental values, via this linear relation here. Okay, now on the importance of K-factor, basically, well, it's quite easy to see from here. So let's say marketing team knowing that, well, if we invest in some campaign, in this amount of money, we'll get this this number of additional paid registrations. This gives us this additional information. Not only will have this directly tracked registrations, but also some extra number of non-tracked registrations, but that are really thanks to the marketing campaigns. So it lets us to compute, calculate the fully profitability of marketing campaigns, of course. And then also it can help us optimize marketing spend. What I mean by that is that this K here, K-factor, can depend on a country. And then, well, having these values for different countries can help us optimize spend across different countries, of course. All right, and now the approaches to this problem. So again, I'll present two approaches. So first one is based on simple time series differentiation, and then the other one based on time series decomposition. So I mean, if you don't know these things, don't worry. Well, you'll see this what I mean by this shortly. Okay, and now so the first approach, as I said, time series derivative. So how does it come up here even? Okay, I can skip this one. Basically, these things I'll be saying here anyway. So imagine you have daily, first of all, we have organic registrations. So you have daily data for organic registrations. You can imagine it being something like this. So this is like in some time period, this is basically time, and this is on y-axis the number of organic registrations, all right? And now, so we have this daily data, but also assume that we have daily data for the number of paid installs, paid registrations, so similar as for the organic. And now we'd like to understand the relation between these two. But we don't really want to understand the relation between these two directly, but rather between these incremental values that I mentioned. So we really want to, so this is how this derivative comes up sort of naturally. So derivative is simply the difference between, sounds fancy, but it's just taking the, subtracting like two consecutive, so taking the difference between two consecutive values in these two time series. So that's how we get these deltas by this transformation. And now what I'm saying is that by understanding the linear relation between these two, we actually can understand, we can approximate the K-factor. So what we're doing is just by fitting a linear regression model, we sort of approximate the delta organic registrations with delta paid registrations via this weight W and possibly some bias B. And now the thing is that this is basically some approximation of our K-factor for the period of time we're considering. And now just, what we did in the previous slide is time series differencing, but this basically came up quite naturally. And also just to say that we have this bias term that can be, well, you can use it or not. If you use it, it's basically like saying, we have some global trend in the time series, because, well, derivative of bt is b, so this is like having some global trend across the time series. All right, so this is the first approach for that, which is the one that is simpler, I think. And now the other approach I wanted to present is based on time series decomposition. So as you saw, like before we took this derivative, which is kind of saying we kind of get rid of if you have any seasonality, if this time series or something like that, we basically say we take the derivative and just forget about them. We just have this global trend maybe, but except for that, we get rid of all other time-dependent factors. And now the other one is kind of a bit more, instead of doing that, let's try to decompose our time series of organic registrations more carefully. And here we have this assumption that, well, all these factors that come into our decomposition, we kind of assume that we consider all the important factors. So there is nothing outside of it that is impacting our time series too much, at least not to prevent us from estimating the k factor. And now the thing is that if we decompose organic registrations into, say, trends, seasonality, maybe some holidays, special events, then we can also add paid registration as yet another factor to our decomposition in some way, as you will see shortly. And then from that decomposition, one can just extract the k factor, basically. All right, how are we doing with time? All right. So by the way, what I'll be presenting like in this next couple of slides are taken from Facebook profit decomposition. So Facebook has this library for decomposition of time series, which is called Profit. But just wanted to say here that you could use any other model or library for anti-series decomposition. It's not really important. I mean, just one example of such a library here that we're using. All right. So once again, our idea is the following. We have organic registrations that you would like to understand in terms of decomposition. So we'd like to fit some time series model through it using this decomposition. So we have some trend, we have possibly some seasonalities, and maybe some other factors like holidays, special offers, events, and stuff like that. And basically the idea is, fortunately, I don't think I'll have time to get very into too much detail of how the decomposition work, but the basic idea is that we have this, we want to reduce it to a linear regression problem. So basically it works by constructing variables, so features for this linear regression, one taking care of trend, where we have potential trend change points as the feature. So this you see that the trend, it's not a coincidence that basically we assume that the trend is like a simple piecewise linear function that doesn't change too often, doesn't change the slope too often. And then seasonality is taken care of with some Fourier terms like sine and cosine functions. So basically carefully construct features for this linear regression problem. Maybe we use some one-hot encoded holidays and special events and stuff like that. We get this linear regression problem and that we solve, and this is how we obtain our decomposition. So unfortunately, I'll be happy to answer questions you have regarding this decomposition. But as I said, this is just one example of a decomposition. It's kind of more important to see how one can apply it later on. And then, as I said, we decompose our time series of organic registrations into trend, seasonality, holidays, and stuff like that. And then, since we reduce it to a linear regression problem, we can just add paid registrations, so the number of paid registrations, as yet another feature to our model, to our linear regression. And then by fitting this linear regression, we obtain some coefficient, some weight standing at the number of paid registrations as a feature. And then by extracting this coefficient, we simply get an estimate for the k factor. So it's again similar idea in the sense we do some linear regression and extract the coefficient and treat it as our k factor estimate. It's just that maybe this way is a bit more complex way of expressing what we are estimating here. So one was, if remember the previous one, differentiation, and here's exact decomposition of the time series. But at the end, we extract the k factor exactly in the same way. All right, so all good. We have this k factor estimates. I presented like two methods for that. But now how do we actually validate k factor estimates, you could ask? And now the kind of pessimistic answer that cannot really be done, in the sense that there is no real ground truth, so it cannot be validated exactly. So I just listed here some ideas how you can approximate it, or how you can maybe increase your confidence that what you're doing makes sense. So first of all, for instance, for this time series decomposition model, it can be also used for forecasting, of course, and then by tracking predictive performance of this model, you can, well, gain some confidence that what you're doing makes sense, including the factoring out the number of paid registrations. Then what you can also do, well, I presented 2 different models. You can maybe use 2, 3, or 4 different models, and then by combining and comparing the inferred k-factors from these models, you can gain some confidence into how the distribution of k-factor looks like and to estimate its value. And now the last idea is kind of maybe sounds the closest to extracting the ground truth. K-factor is basically, say I choose some country and I pause all marketing campaigns in this country. If k-factor is non-zero, we expect a drop in organic registrations as well. And basically, but estimating this difference, this drop that we get, we can estimate the k-factor. Now the problem with this, that is actually quite expensive to pause all marketing campaigns. So you typically would do it maybe for a couple of days, and then it's kind of questionable whether this k-factor you obtained for this, I don't know, 3 or 7 days, whether it really reflects your average k-factor for the whole year, first of all. And say if you want to prolong this experiment, then maybe then it actually becomes increasingly more important to have some kind of counterfactual estimate of what would the number of paid registrations, organic registrations be, have we not paused all paid registrations, all marketing campaigns. So that by comparing this like kind of fake ground truth with what we actually see in the data after pausing marketing campaigns, you can again measure the k-factor somehow. This can be, by the way, done by some models like causal impact model that is implemented in R. But again, this is just involving more complexity and kind of less certainty because of that. But again, it can be, in theory, it can be done. All right, and just to mention, like, this is it for k-factor. Just to briefly mention, like, these areas, sub-areas of predictive modeling that we didn't really have to talk about in detail, just to mention them briefly. So we have, for instance, marketing mix modeling, which is basically understanding, so again, this is all applied to marketing, so understanding some key metrics, in this case in mobile gaming, like registrations or revenue, as functions of marketing spend. So of course you have some ads, let's say on Facebook, you can always put more money to bring more users, but at some point you won't be, so like the curve that you get, like users you get, you won't be, I mean, you have some saturation basically, so you won't be able to get infinitely many users, but putting infinitely many money, but just like you have some saturation of this curve of all users you can get. And this is like kind of this plus time series decomposition, it's what marketing mix modeling is all about. So it's again about understanding this relation of marketing spend and some key metrics. And the nice thing about this is that it uses only aggregate metrics. So it's aggregate number of registrations, aggregate revenue, which kind of doesn't make use of like any data privacy. So it's very important, like in light of privacy restrictions on iOS, this marketing mix modeling becomes a hot topic recently. Now I have pair prediction, which is like similar to LTV prediction related to transactions, but here we just want to predict whether a newly registered user will become a pair after some period of time, and this is often used in like directly optimizing marketing campaigns, for instance. And then we also have churn prediction, which is predicting whether a user will become inactive in a like short period of time, and this can be used for retaining users, potential churners in the app through some notifications or offer something like this. Okay, so this is basically it for the technical part. Just the last site I prepared here is regarding some hiring opportunities. So you can always check out open positions at our careers website. Also make sure to check out our early talent program that is directed towards students. We also recently posted the Nordeous coding challenge on our LinkedIn page involving this data science challenge with some cool prizes. And of course, if you have any questions regarding the presentation, you just want to reach out or have any questions regarding some hiring opportunities, feel free to contact me at this email address. So my first name and the first letter of my second name at Nordeous.com. Okay, so that's it. Thank you so much.
Hello.
Hey.
Thanks for the presentation. I have two questions regarding LTV. I'm not understanding the motivation of using daily samples for the users. Wouldn't it make more sense to sample by mobile app releases or marketing even campaigns? That's the first question. And second question is, wouldn't it be more sensible to track amount spending and the user usage of the application? So you want to optimize each user to use the app more and more, and as well as spending more.
So the first question is regarding, because I said we have daily data, so all the users register on the same day. So of course, yes, in practice you're kind of more interested in the sense that you don't want like a single user, but a group of users. But it's true. You rarely really use it on daily. Maybe use it on weekly level.
No, I mean maybe even
like
or release if you are doing sprints like in 2 weeks, and then group the users by 2 weeks rather than for every single day.
Of course, we use it on various for various intervals. So actually, it's rarely exactly 1 day. It's more often 1 week. Or maybe 28 days, because this is the length of the top 11 season, or 1 month or something like this. So of course, yeah. And the second question was regarding the...
wouldn't it be more sensible to optimize not only the spending of the user, but spending and time spent in application for each user?
So yeah, of course, in some sense, so kind of game design is kind of, as we had some talks today, like about users' engagement, and of course we in Nordeous track these metrics. But with regards to marketing, kind of what marketing is concentrated on, whether they invest some money and they just want this money back, to put it simply. So it is important, but not maybe in this context of marketing, because if you wish, in some sense, anyway, in the model we kind of have one parameter, meaning transaction frequency, but the other also like kind of activity. So we really, in the end of the day, we care about spend, but often as a byproduct, of course, if you want users that spend a lot, they also have to be active in the game. So, but in the in this marketing perspective, you actually look at how much they spend in the end of the day.
Thanks.
Sure.
Do we have any more questions? Okay, one in the back.
Hi. Regarding first part of the presentation, Pareto MBD model, there are a lot of people with basically zero purchases, right? And when you fit the graph, basically you fit distribution to your
it's actually, sorry, this one is not Pareto NBD, but a variant of it, basically.
Okay, yeah.
Yeah.
What I'm saying, like a beta-gamma distribution does not fit well to group of users who have like so much of one group of zero, and then everybody else has kind of distribution, right? How do you manage that?
You mean, okay, there are a couple of things you can do. So basically what we do also within our model, so how this model is defined really usually, it's, well, you can either you can take all the users who registered, but you can also look at the number of first, so we can basically filter all the paying users by taking just only the paying users, so to say. So actually in the model, there is some step that we have, so it's not like without bells and whistles, we have to be a bit careful to treat these users, so kind of we have a separate estimate for the users that registered but still didn't have any transactions, so to say.
Okay.
Yeah,
so basically you have two models, one for users who...
Kind of, yeah. It's like,
okay.
joint two models in some sense. They have to be taken care of a bit differently, as you're saying. Yeah, thanks.
That's it. Thank you for the great presentation.